So our next session is software-driven tinyML hardware co-design. So let's welcome our speaker, Weier Wan. He's the head of software hardware co-design at Aizip. Dr. Weier Wan is currently leading the software hardware co-design and is a founding member at Aizip, a Silicon Valley startup providing tinyML solutions. He received his PhD degree in electrical engineering from Stanford University in 2022, where he worked on designing efficient AI hardware system to enable intelligence at the edge. His research work has been published in top journals and conferences, including Nature, International Solid State Circuit Conference, and Symposium on VLSI Technology and Circuits. He is the first author on monumental work published in the Nature this year, titled A Compute in Memory Chip Based on Resistive Random Access Memory. Previously, he received his master's degree in electrical engineering from Stanford in 2018 and his bachelor's degree in physics in electrical engineering and computer science from University of California, Berkeley in 2015. Let's see what he has in store for us. Over to you, Weier.
All right. Yeah, so thank you for the introduction. Good morning, everyone. So today I'm going to talk about the work that we've done to push the frontier of tinyML software and hardware co-design. So today, the AI-powered smart devices has already been pervasive in our lives. So the applications range from smart homes, smart wearables, and smart IoT sensors. And many of these devices have at least part of the AI algorithms running locally within the devices themselves. So this brings many benefits, such as lower latency, better data privacy, less energy consumed at wireless data transfer, and of course, lower cost associated with the cloud services and internet. So deploying AI algorithms at the edge has to meet the stringent requirements of power and cost, and especially for these battery-powered devices, where the energy efficiency is really the key. So over the past few years, this tinyML community has made tremendous progress to make both the algorithm and the hardware more efficient. So in terms of the algorithms, the tinyML model designers are essentially solving a constrained optimization problems where the constraints are the limited hardware resources, including the RAM size, flash size, the available compute throughput, and the supported neural network operators. And the target is oftentimes to either lower the latency or to get better accuracy. And of course, depending on the specific application requirements, these constraints and the targets can many times be interchangeable. So some commonly used techniques to make AI models more efficient, including use efficient model architectures, quantizing models to lower bit fixed point precisions, pruning, neural architecture search, and last but not the least, writing faster and less memory consuming kernels for commonly used operators. So here I would like to show by data how the efficiency of the models have evolved over the years. So here I plot the ImageNet classification accuracy versus the number of parameters for many different neural network models. And the upper left corner is the one we would like to be at. So essentially a higher classification accuracy at less parameter count. So all these data points shown here were from papers published before 2020. So this blue curve here represents essentially the Pareto optimal curve at a time. So now we add more data points from those papers published after 2020 and look at these new Pareto optimal curve. And we can have two interesting observations. So first, on the far right side of the plot, many of these more recent studies show that the accuracy can still scale pretty well with the model size. So these giant models with billions of parameters can now achieve an accuracy higher than 90%. And second, on the far left side of the plot, we see that the models are becoming much more parameter efficient, right? So for example, to reach a 70% top line accuracy, before we need around 4 million parameters, whereas now we only need around 1 million. So that's about 3x reduction in model size. And of course, the number of parameters is not the only measure of the efficiency of a model, but it gives us a good idea. So there has also been lots of effort in designing more efficient tinyML accelerator hardware. And typically the design starts from designing a set of models it wants to accelerate. And meanwhile, under the limited resources at the edge, the hardware design is always about making the right trade-offs. And in tinyML, all these 5 characteristics are important, and they're actually tightly correlated with each other, right? So they include the power, area, flexibility, latency, and accuracy. And driven by both the models and the applications, the accelerator hardware design involves the design of the data paths, where you need to decide the operators to accelerate, the number of parallel units and the precision for each operator, and the memory design, where you need to determine the number of cache levels and the size of each cache levels, and finally, an instruction set to operate the entire data path and the memory. So this field has also been moved at an incredible pace. So today, some of the state-of-the-art NPUs, which stands for neural processing units or AI accelerators, can already achieve an energy and area efficiency almost 4 orders of magnitude better than the CPUs. So some most efficient ones can already achieve roughly 10 TOPS per watt of peak energy efficiency and 100 GIOPS per millimeter squares of peak area efficiency. And of course, it is not to say that these NPUs are always better than CPUs or DSPs in every aspect. So as I show in the previous slides, so other factors such as the flexibility and the cost sometimes matters more. So we've made a lot of progress in building efficient models and efficient hardware. And all these techniques that I've mentioned are typically referred as algorithm hardware co-design techniques. And to further improve the tinyML systems to allow more complicated AI tasks to be done at even lower power consumption and a lower cost, the models and the hardware need to be even more tightly co-designed. So currently, there is still some disconnect between the model design and the hardware design. So in terms of the model design, most efficient models are optimized for the number of operations and the number of parameters. So these metrics are a good proxy of efficiency when deploying the model onto CPUs, where the processing is mostly sequential and when there is little room for data reuse. However, these models might not necessarily deliver the best efficiency on NPUs, where the processing is much more parallel and when there's a lot of data reuse can be used. So besides, these efficient models can be more difficult to quantize without losing accuracy and can be more affected by the non-idealities of the analog hardware, which I will discuss later. So in terms of the hardware design, know that when I talk about the 4 orders of magnitude efficiency improvement, I use the word peak efficiency, right? So this peak efficiency is usually measured on doing dense and low precision Mac operations only, with 100% hardware utilization and with a very specific memory access pattern. So unfortunately, this is rarely the case for real workloads. So in real workloads, we can have many sparse or vector operations, and we might need high precision at some sensitive layers, and they result in low utilization and more complicated memory access patterns. So many times we could observe that the end-to-end system level efficiency is much lower than the peak efficiency on a paper. So besides, the lower latency or lower power is not always important, right? So sometimes we might want to sacrifice them for a lower cost, depending on the specific application needs. So here at Aizip, we would like to overcome these co-design challenges. So Aizip is mostly a tinyML software company. So we're based in Cupertino, California, and we provide production quality tinyML models and software to our worldwide customers. So although so far we have focused primarily on the models and the software, we also have researchers and engineers with deep expertise in hardware design, particularly the AI accelerator design. So it's our vision to design tinyML solutions with the best efficiency, robustness, and cost by jointly co-optimizing algorithms and the hardware. So this means that we not only use our tinyML models to guide the hardware design, but also we optimize the model architecture and the training method for specific hardware platforms. So currently, we do not make our own hardware products. So instead, we partner with IC companies and provide co-design services to our IC partners to develop industry-leading tinyML hardware products. So this co-design service leverage our broad portfolio of tinyML models spanning various vision, audio, and time series applications, such as visual wake word, object detection, face recognition, keyword spotting, speaker ID, noise reduction, human activity recognition, and predicament maintenance. So our co-design services cover both the conventional digital accelerators and the emerging analog processing in memory accelerators. So for our IC partners, no matter which kind of accelerators you want to develop, we can support you, and our team members have expertise in both. So comparing these two kinds, they each has its own unique advantages. So for digital, they are robust to hardware non-idealities, whereas the analog PIM accelerators can be more affected by non-idealities, such as PVT variations, nonlinearity, and noises inside the analog circuits. And also, the digital accelerators have a more mature and more automated design and verification process, which often leads to generally faster product development time. And they're also more scalable to advanced technology node. So on the other hand, the analog PIM accelerator can be more energy efficient and can use less chip area. So that's why we think they are a perfect fit for many battery-powered tinyML applications. So next, I will dive a bit deeper into PIM and explain why it can be more efficient and what our PIM co-design services will provide. So here is a simplified view of a typical digital AI accelerator chip, right? So the chip houses an array of processing elements or PEs, and each PE consists of several multiply and accumulate units, and ALU for other operations, and some local SRAM. So the chip also has some global SRAM that is shared by all the PEs, and embedded flash to store model parameters and programs codes, right? So now if we compare the energy consumption from each of these components, MAC is actually the cheapest, and the SRAM access are around 10 to 100 times more expensive, and the flash access can be 1,000 times more expensive. So really the key for energy efficiency is to reduce the memory access. And here I will use the SRAM to illustrate the memory access process, right? So these yellow rectangles represent an SRAM array with M rows and N columns used to store neural network weights. And to read it, we use the decoder to select one row of SRAM cells at a time, and then we can use these sense amplifiers to read the values of the selected row. And these values will then be sent to the PE arrays for processing. And because the memory access happens sequentially, one row at a time, it will take a total of M cycles to read the entire array. So the total energy consumption will be M times the row energy plus the M times N times the column energy, where the column energy consists of bit line energy, sense amplifier energy, and the wire energy, plus the MAC energy, right? So now in processing memory, again, we can use the SRAM cells to store the model weights. But instead of reading one row of SRAMs at a time, we can simultaneously turn on multiple rows. And this is really the key difference. And we can even send different multi-bit values to different rows by connecting each row to a separate DAC. And then the multiplication between input and weights is performed locally by each SRAM cell, and the accumulation is then performed along the columns using analog computation. And the final multiply and accumulate results are converted to digital values by ADCs. And due to this parallel processing, each column is only used once rather than m times, right? So this saves bitline energy. And more importantly, because the MAC operations are performed directly inside the array, we eliminate the energy consumption from both the wires and from using separate digital MACs, right? And this also reduces the chip area by eliminating the digital MAC units. So due to its promises to improve both the energy and area efficiency, the processing in memory has gained lots of tractions in recent years, and we see the number of PIM test chips presented in the ICC conferences has grown steadily over the years. And to go from these test chips to actual products, the hardware design alone is not sufficient. So from bottom up, we need to optimize the model architectures and the training strategies to account for the specific hardware characteristics, such as the hardware non-idealities and utilization rate, right? So from top down, we also need to design the SoC architecture to be efficient, not just in multiply and accumulate, but in executing the entire model, including any input data pre-processing. So here at Aizip, we provide full stack PIM code design services, right? So first, we have the charge domain SRAM PIM silicon IP. So there has already been many different implementations of SRAM-based PIM. So the test chips that came out the earliest mostly adopt the current-based design, where the MAC operations are performed through current summing. And these current-based designs typically exhibit large nonlinearities and are sensitive to variations. So the computation accuracy is a major concern. And this issue can get even worse at more advanced technology nodes. And in addition, the current-based design needs to use large peripheral circuits in order to sink the large current. And this makes the design not so area efficient. So to address these issues, the charge-based design has emerged as an alternative. It performs MAC operations through charge sharing among capacitors. And in general, they're more robust to non-idealities and scale better to advanced nodes. But one downside is that the first several charge-based test chips all need to use customized 8T or 10T SRAM cells rather than foundry-provided standard 6T SRAM cells. And this could lead to lower area density. So more recently, we have seen designs that combine the best of both worlds. It not only uses robust and efficient charge domain computation, but also can use foundry-provided standard 6T SRAM cells, which are 2 to 3x smaller than a customized 8T or 10T SRAM cells. So Aizip was licensed such a charge domain 6T SRAM PIM IP from Rice University, and we provide IP to our customers through the sub-licensing. So the IP was named the CAPRAM and was invented by Professor Kaiyuan Yang's research group and was validated using a TSMC 65 nanometer process. And the results were presented in their JSS paper last year. So on top of the IP, our design services also covers accelerator architecture design, right? So the design will integrate the PIM IP and all the other necessary compute and memory modules into a complete accelerator system that can support end-to-end deep neural network inference. So generally, we would first provide our customers with a reference design, and then together we will customize the design to meet specific application requirements. And as discussed earlier, the PIM and digital NPUs each has its own pros and cons. And in terms of their efficiency on different neural network operations, PIM is more efficient on low precision and dense tensor operations, whereas digital is more efficient for higher precision and sparse or vector operations. So many neural network models, especially those ones that are optimized for efficiency, contain both types of operations. And therefore, our accelerated design combines both types to maximize the system level efficiency. And finally, we have PIMNet deep neural network models that are designed to realize high utilization on PIM without increasing the number of parameters, and a PIM-aware training framework that can train PIMNet to be resilient to both quantization error and analog hardware non-idealities. So although there has been lots of work on efficient model architectures, to date, very few PIM test chips have attempted to use these efficient models. And the reason is that these efficient models has low utilization when mapped onto PIM accelerators. So the model level efficiency cannot really translate into real hardware efficiency. And another reason is that these efficient models are typically more difficult to quantize to low precision without losing accuracy, and are more sensitive to hardware non-idealities. And on the other hand, although these unoptimized dense neural network models can achieve a higher utilization on PIM and is generally easier to quantize, they are many times over-parameterized and therefore need large SRAMs. And these can offset the efficiency benefit of PIM. So really for us, the question is, can we simultaneously be parameter efficient, high utilization, and accurate? And our results show that this can be achieved by combining the PIMNet and the PIM-aware training, right? So for example, on the ImageNet classification, our PIMNet model has similar number of parameters and can achieve similar accuracy as MobileNet V2. But what's different is that the model can also achieve a utilization rate higher than 80% on the PIM array, and it can maintain its accuracy to above 70%, even when considering the impact of 4-bit quantization and hardware non-idealities. The similar results was also obtained for other applications, including visual wake words and keyword spottings. So these are simpler tasks compared to ImageNet, so their corresponding PIMNet models use less parameters. And to recap, from silicon IP to accelerator architecture design and to tinyML model design and deployment, Aizip can offer a comprehensive list of PIM co-design services. And as a result, we can support our IC partners during the entire product development cycle. So in summary, the algorithm hardware co-design has been proven to be essential for tinyML systems. And going forward, the algorithms and the hardware should be co-designed even more tightly than today, so that we can continue to push the frontier of tinyML. And in addition, a tighter co-design means that the application level requirements can be more directly mapped onto hardware design parameters. And this will help us to make the right design trade-offs and to build more customized tinyML systems. So this is the end of my talk, and thank you for your attention. And let me know if you have any questions.
Thanks so much, Weier, for the very insightful session about algorithm design for lower latency, better accuracy. We have a question from Hyunjin Kim. He actually is asking about a high computational layer can be critical in a neural network, but not in another neural network model. How can the layer be evaluated between different models?
Right. So I think so my answer has two parts. So first of all, generally when we have application, we start not from the model, but really from the application requirements. So that means for some applications, if the best solution is to use neural network with high computational layers, then we would pursue that route. But if there are other approaches, for example, using some more traditional signal processing techniques that are better suited for that application, we would, of course, first consider these more efficient alternatives, right? And the second part of my answer is that, as I show in my slides, really, in terms of the accelerator design themselves, different types of accelerators can be suitable for different types of neural network layers, right? So for those most computational intensive layers, maybe it's better to be mapped onto the parts that suited it to the best. But for other less computational intensive, but those layers that might require higher precisions, we might want to map it onto different part of the hardware. So really, the accelerator design should try to answer this question from the system perspective, rather than trying to map the entire workload onto one single places on the hardware.
Awesome. Thank you so much, Weier, for all your responses and your session.
Good. Once again, we want to thank our sponsors, Tiny Edge Impulse, one of the leading what's called platforms for Edge ML and using tinyML applications. Our executive sponsors, Qualcomm, who have advanced AI research to making efficient AI ubiquitous, both hardware and software. Cintiat, accelerating your edge compute. Platinum sponsors, DeepLight, fastest video analytics solutions on ARM CPUs. Kilkatech, global IoT solutions. Renesas, basically big ideas for every space. The Sony Semiconductor Solutions Corporation. Gold sponsors, Analog Devices. ARM, who also have their own talks, so please feel free to sponsor them and jump onto their line as well. PhotoHub, making over-the-air firmware and model updates simple and accessible. That's probably one of the key things moving forward, so have a look at PhotoHub. Microsoft, for their edge capabilities and technologies, including all their, Azure services to support tinyML. NXP, together accelerating breakthroughs that advance our world, a great hardware provider. SensiML, analytics toolkit suite to be able to do your AutoML capabilities. STM Microelectronics to provide extensive solutions to make machine learning easy. Synaptics, engineering exceptional experiences. And then a list of silver sponsors, including Aizip, Aeon Devices, EMSA, Greenwave Technologies, Gravity Inc., IBM, Imagimob, Etermis, Nota AI, OctoML, Prophecy, Quexo, Rexon, SAP, Silicon Labs, Stream Analyze, TDK and Vincent. So thank you once again for attending. I hope to see you tomorrow online to listen to some of those interesting presentations. And thanks to everyone. See you soon.